Hey ladies and gentlemen, welcome to this video on systems of equations. We're going to be looking at how to solve systems in this and what a system of equations is. I'm looking at my toolkit entry here. Mine is at the bottom of page 42. Again, yours might be a little bit earlier than that in your toolkit if you have one of the newer ones. But we're looking at systems of equations vocabulary to talk about what a system of equations is. Feel free to pause the video at any time if you want to copy down the notes that you're seeing. A system of equations is any situation where you have more than one equation. And to find a solution to that system, we're trying to find the one or more solutions that are common solutions between all the equations. So first off, taking a look at the graph that they show you here, a solution on a graph is going to be this point of intersection, because if we think about what a solution is on a graph, a solution is all the points on the line. So for Rio de Janeiro here, we've got all these points. There's an infinite number of points in this line. All those infinite number of points represent solutions for that situation. All right. San Francisco, same thing. There's an infinite number of points on this one here. All represent solutions for that equation. However, there's only one point that we see right here that's on both lines. This is our point of intersection. That one point is what makes both the equations true. And that's what I have written over here. These two pieces are the real keys that come from this whole toolkit entry, and that is that a solution to a system of equations is the intersection point. It's the point that makes both equations true. We will just be looking at a system of two linear equations in this class. As you go into the future, you'll realize that you can have systems of nonlinear equations, you can have systems of more than two equations, and so on. But we're going to be looking at just a system of two linear equations. With that in mind, let's take a look at the study island lesson. Here in our study island lesson, we can see that a system of equations has exactly one real solution if the two lines intersect at a single point. That's what we just said. We're looking at that one point where the two lines cross. The solution is the point where the two lines intersect. The graph of such a system of equations is shown below. Note, two lines with different slopes will always have exactly one solution. Basically, they're saying if the two lines have different slopes, they're going to intersect at one point, and that one point is the solution to the system. Again, there's an infinite number of points on both lines, but there's only one point that's on both lines, and therefore there's only one point that will make both equations true. There are two special cases with solving systems. Just like solving linear equations, we came up with no solution in all real numbers. The same can happen with a system. A system of equations has infinitely many solutions, or all real numbers, if the one equation is a multiple of the other. In such a system, both the lines coincide as shown below on the graph. All right, note that the two lines with the same slope and same y-intercept will always have infinite number of solutions. Basically, what they're saying is they did graph two lines here, but they are the same line. All right, both of these are the same exact line. All right, an example would be like y equals 3x. Well, actually, I'll just give this example here. All right, so my example here, this equation is y equals negative x plus 3. But another way to look at this equation could be 2y equals negative 2x plus 6. So we just multiplied everything by 2, so it's still the exact same equation. Another version, if I just added the same thing to both sides, I could say y plus 2 equals negative x plus 5. I just added 2 to both sides. It's the same equation. I just added the same thing to both sides. So if you happen to have two lines that are exactly the same, they're going to overlap. And therefore, every single point on that line is going to be a point on both lines, because technically both lines are the exact same line. That's why there's infinite many solutions. You'd write your answer for this just like we would on a standard equation, x equals all real numbers, because x is our independent variable, or you could just write all real numbers. Let's take a look at the bottom one here, our second special case. A system of equations has no solution if the two equations are parallel lines, as shown in the graph below. Note that the two lines with the same slope but different y-intercepts will always have no solution. So in this case here, we've got y equals x plus 3. That is my red line. And my blue line here is y. I'm drawing two lines there. All right, my blue line is y equals x minus 1. Notice that both of these have the exact same slope, My slope in both of them is 1. That's what makes them parallel. And parallel lines will never cross, so there's no point that's on both lines. Therefore, there's no point that will make both equations true. Therefore, there's no solution. We could say x equals null in this case, just like we do for a standard equation that we solve. And again, we say x equals null because x is the independent variable. All right? So these ones all have no solution. Now let's take a look at how to solve things algebraically instead of a graph. All right? Because often, you're not going to graph the lines. I'm actually going to ask you to solve the system of equations algebraically. Now my toolkit entry that follows this one, if I just scroll down, I see I get the equal values method. The equal values method is the first of our algebraic methods that we're going to teach you. There are 3 algebraic methods you can use to solve a system of equations. This one is the first one. All right. Now they give you an example here, but one thing that I did was I actually wrote the problem down on the right-hand side. All right, so I wrote that down right here. They said the problem in here, it said start, I'm looking right here at step 1, it said start with the 2 equations in y equals mx plus b form, slope, intercept form, such as y equals negative 2x plus 5 and y equals x minus 1. That was the problem, but it wasn't very clear, and it kind of looks like that was the problem, and that would be confusing for you. So I would encourage you, please write down the original problem. When you write down the original problem, you would write something like solve the following system or solve the system, and they're going to give you 2 equations like this. All right, and they're given in slope-intercept form when we're using the equal values method. They're both going to be set equal to the same variable. Typically, that's y, and that's what we're going to be using in this class. It could be x in the future, but right now we're going to focus on the fact that it's set equal to y. So we have y equals 2x minus negative 2x plus 5, and y equals x minus 1. And I want you to solve that system of equations algebraically. So, step number 1, start with the equations in that form. That's done. Notice I marked step number 1 here and step number 1 here. Step number 2, I highlighted it. Set them equal to each other. That means set the 2 non-similar expressions equal to each other. The reason we can do this is because of the transitive property of equality. The transitive property of equality says if A equals B and A equals C, then B must equal C. Basically, if negative 2x plus 5 is equal to y, and x minus 1 is equal to y, well then negative 2x plus 5 must equal x minus 1. That's what we're doing here. We're just setting the 2 non-y expressions equal to each other. And that's what we see right here. And that's why I marked this part right here as step 2. Once we do that, at that point, now we have ourselves one equation with one solution, one equation with one variable that we can solve. And we can solve that the way we do any equation. And in this case here, they subtracted x from each side and then subtracted 5 from each side. And they got negative 3x equals negative 6, and then they divided by negative 3, divide by negative 3. They found that x equals 2. Once I find my first variable, now I'm going to step 3. And that is substitute your solution for x into either equation to find y. They picked our first equation right here. They just picked negative 2x plus 5. And notice what they put in for x. They replaced x with 2. That's what we found x was. So therefore, I can now plug that in, and I simplify, and I found that y is 1. So step 4. A good way to check, which you should always check your solution, is to substitute your solution for x into both equations and verify that you get the same y value. Well, I know it worked in this equation, negative 2x plus 5, so I have to check it in this equation, the other equation, x minus 1. And notice we plugged in 2, all right, and 2 minus 1 is 1. Notice we got the same y value. These matched. That's what tells us our answer is correct. It worked in both equations. The x value of 2 got me a y value of 1 in both equations. So then we just write our solution. We'll always write it as an ordered pair x comma y. In this case, that ordered pair is 2 comma 1. That's our toolkit entry. All right, that's the example they give you. If you want more examples, I'm going to go show more examples right now, and you can copy those in here. You could put them either on the side over here in this area, or you could put them on another page if you need to. But before I do that, I just want to show you the bottom piece here, because it's going to reiterate what we've talked about earlier. All right, solutions to a system of equations. Remember what we said. Sometimes there's special cases. Most of the time, you'll get one solution. All right. And if you notice down here, we've got a solution to a system of equations gives a value for each variable that makes both equations true. That is important. I would go ahead and I would highlight that section right there. All right, makes both equations true. For example, when 4 is substituted for x and 5 is substituted for y, both equations at the right, they just gave a new example over here, all right, are true. Now some equations, I'm looking down here now, some equations have no solutions or infinite solutions. Consider the following examples. Notice that the equal values method would yield 3 equals 4. All right, now they're not showing us the equal values method, but basically they're saying that these would have no solution if we solved it. We would get the variables drop out and get an untrue statement. All right, and therefore it has no solution. All right, and it's not true. In this case, we would write x equals null. All right, and the third set, these would be parallel lines. They're going to get a true statement, so we'd find there's infinite solutions. We could write x equals all real numbers. This is basically what we've been doing with solving equations. And in that first step, when you get the equation with one variable, when you go to solve it, if you get one answer for x, it's one solution. You keep going, and you get it by plugging it back in and getting y. If you go to solve it and the variable drops out and it's an untrue statement, it's no solution, just like it's always been for solving a linear equation. And same with all real numbers. It's the same as it's always been. The only difference with a system is what it means. If there's one solution, the two lines will intersect, as we saw. If there's no solution, they're parallel. All right, so it says no solution is parallel lines. And if they're infinite solutions, then they're coinciding lines, which means they're the same line. All right, now on to some examples. All right, let's take a look at this example here, number 1. First off, I notice both are in slope-intercept form. Both equations are set equal to y. Therefore, if negative 3x plus 4 is equal to y, and 3x minus 2 is equal to y, then negative 3x plus 4 must equal 3x minus 2. It doesn't matter if you switch those and put them on opposite sides, that's fine, as long as one is on one side, one is on the other. Now we have one equation that we can solve for x. I'm going to add 3x to both sides to solve that way. And I'm going to add 2 to both sides. If you're struggling with solving equations, this is going to be a little confusing for you, so go back and learn that skill. All right? If you're able to solve equations, then this should make complete sense on how I got to x equals 1. Now, that's not my final answer. There's 2 variables in a system. That's only one of them. I need to go back and find the other. Now, I use either equation. It doesn't matter. I'm just going to take the first one. All right? So I have y equals negative 3x plus 4. And I'm going to take this x value and I'm going to plug it in. So y equals negative 3 times 1 plus 4. That's going to be negative 3 plus 4, so y equals 1. All right, so now I have x, I have y. I want to make sure that they work. So I'm going to check them in the other equation. If I use the first equation to find y, I've got to use my other equation to check it because I have to make sure it works in both equations. So I'm going to take this one here. I said y is 1. All right, equals 3 times, I said x was 1. In this case, I'm saying they're both 1. All right, minus 2. Let's make sure that works. Well, this is going to be 3, and 3 minus 2 is 1, and it works. All right, that tells me my answer is correct, so I can write my answers in ordered pair. My answer would be 1 for x, comma, 1 for y. They're both 1 in this case, but let's show you why that's true. Let's look at our graph. All right, just for color coding's sake, so you can follow me, I'm going to color code these. All right, I'm going to make this one here red. All right, now I see it's got a y-intercept of 4, so I'm going to start at 4 on my y-axis. And I see it has a slope of negative 3. All whole numbers can be over 1. Negative means down 3 over 1. Down 3 over 1. And down 3 over 1. And from there, I'm going to get myself a line. Pardon me that I can't use a ruler on the screen. You should definitely use a ruler. All right, but there's my line, y equals negative 3x plus 4. Now I'm going to go a different color. Let's go green. All right, so here we go here. Y equals 3x minus 2. That means my y-intercept is negative 2, so I'm going to start at negative 2 on the y-axis. My slope is positive 3, so 3 over 1. Positive means up 3 over 1. All right, up 3 over 1. And I can get my line at that point. All right, again, I apologize, it's not straight, but notice what we see. Notice here the intersection point. The one point that's on both lines is 1, 1. That was exactly what we said our solution was. That's why a solution to a system of equations is the intersection point, and it's the one point that makes both equations true. Let's take a look at another example. All right, here's another example. I do encourage you to go ahead and pause the video and see if you could solve this one on your own before watching me do it. Now, I'm assuming you paused it. Let's go ahead and get started. Once again, I see that they are both set equal to y. Therefore, 3x minus 22. That doesn't look like a 2. 3x minus 22 equals 2x minus 15. Well, if I solve that for x, I'm going to subtract 2x from each side. That gives me x minus 22 equals 15, negative 15, careful. And then I'm going to add 22 to both sides, add 22. I find that x equals 7. Good, that's the first part. Now, let's find y. I'm going to take y equals 3x minus 22, and I'm going to plug in what I found. 3 times 7 minus 22. Well, 3 times 7 is 21. Minus 22, y must equal negative 1. If that's correct, it'll work in my check step. Again, I have to use the other equation to check it. So here I got to check that it works in 2x minus 15. I already know that it works in 3x minus 22. So let's plug it in. Negative 1 for y. I'm going to plug in 7 for x. And I find 2 times 7 is 14. 14 minus 15 is negative 1. Look at that. It worked. It made my equation true. Therefore, it is the solution, and I'd write it as x, which is 7, comma y, which is negative 1. That is my intersection point, the one point that makes both equations true, the solution to this system. Let's take a look at some special case examples. All right, taking a look at this example here, as we see, it looks like it starts the same way. They both set equal to y, and they both start with 3x, but the tail end is different. Right away, I can recognize that these two lines are parallel because they both have the same slope. And that's going to be important here. Let's solve it algebraically as we've been doing. So, as usual, we're going to take 3x minus 7 equals 3x plus 1. And we're going to solve for x. And when we do that, I subtract 3x from each side, and something happens here. My x drops out, and I'm left with a statement. And just like solving a linear equation, as we've always done, we ask, is this true? Whenever your variable drops out, you ask, is what remains true? In this case, the answer is no. Negative 7 does not equal 1, and therefore this will never be true. There is no solution. And we write our answer like that. In terms of the system, what does it mean? It means these lines are parallel. Because they will never cross, they will never intersect. There is no intersection point, therefore parallel, because they're not the same line. Let's take a look at another example. Now this is our fourth and final example for this, and notice I've taken the equations and I just made them the exact same. I want to show you very clearly why this is the way it is. But what we notice here, they're the same line. That means they're going to be on top of each other on the graph, but let's solve it algebraically and just show you what it looks like. If I were to set them equal to each other, you're like, well, of course they're equal. They're the same thing. But if I still solve the equation by moving my x's to one side, my x's drop out, and I'm left with negative 7 equals negative 7. And as we just talked about, anytime the variable drops out, we ask, is this true? Is what remains true? Here in this case, the answer is yes. Negative 7 equals negative 7. Therefore, x can be all real numbers because any value of x will always make this equation true. That means any point on this line is also a point on this line. So they have an infinite number of intersection points. All right, that means they are the same line or the lines are coinciding with each other. All right, I hope that helps. If you need more practice, come see me. Good luck.